Good evening, and a very warm welcome to the second of the W.S. Carlson International Polar Year public lectures. It's really, really gratifying to see so many people here this evening, and thank you very much for coming. Greetings also to those of you who are watching these proceedings on the simultaneous webcast and through Second Life. My name's Fritz Nelson. I'm a professor in the Department of Geography here at the University of Delaware, and I co-chair the Carlson IPY events with Lisa Griffiths of the Center for International Studies. The rest of the committee was shown on one of these slides that was looping around just a few minutes ago, and this series of events absolutely could not happen without their input, and Lisa and I are extremely grateful for their creative and very dedicated service. We're also very appreciative for the support the project has received from the University of Delaware. Our sponsors, as you can see on this slide, include the Office of the Provost, the Vice Provost for Research and Graduate Studies, the Office of Public Relations, the UD Library, the Center for Material Culture Studies, the Academy of Lifelong Learning, I'm almost out of breath here, and each one of the university's 7 colleges. I'm also very pleased to announce that the Carlson IPY project has formed a new partnership with the University of Delaware Museums. Dr. Janice Tomlinson is here to tell you a little bit about that a few minutes from now. It's also very important for us to note that our partner organization in the Carlson IPY events is the American Geographical Society of New York City. AGS is the oldest professional geographical organization in the United States, and it traces its history back to 1851. One of the primary reasons that it was formed was indeed to support polar exploration and to act as an advocate for scientific observation and experiment in all of the many expeditions that it sponsored over the years. This thing's getting away from me here. AGS played a very large role in previous international polar years and was actually the host organization for the World Data Center for Glaciology during the third IPY in 1957-58, which was also known as the International Geophysical Year. The Carlson series involves a wide variety of events: public lectures, departmental and interdisciplinary seminars, art exhibits, films, and special events such as February's globe signing, which I imagine many of you were at. But among all that variety, the Carlson public lectures hold a special status. They're really our premier events because they're meant to be simultaneously informative, highly interesting to all elements of a very diverse audience, and perhaps above all, to be educational. The speakers and the topics are carefully chosen to appeal to an audience that comes from both inside and outside the university. Boy, this thing. Well, excuse me a second. It's the usual thing. I'm going to have to change presentations here. Up. Okay. Yeah. Just has to load and we'll be there in a second. Okay, yeah, here we go. Sorry about that. Before I introduce the real host of tonight's lecture, Tom Apple, Dean of the UD's College of Arts and Sciences, I have to make a little bit of an aside. This is really quite a very interesting thing. This whole business of running a series of events, lectures and films and everything having to do with the polar regions just has shown me how interconnected everything really is. Boy, this thing is really just jumping all over the place, so bear with me. This little aside that I'm speaking of has to do with serendipity and coincidence and just plain good luck. At the introduction to the series back in February, I mentioned briefly how part of the impetus for the series came from meeting another UD faculty member at a very remote field camp in northern Alaska. Neither of us knew anything about the other at all, and we figured we'd better start a campus series so that all of the people with polar interests at this university could get to know one another and begin to act as something of a group. Well, we subsequently discovered that UD has at least 25 faculty and many more graduate students working actively in the polar regions. Well, at the same time, we found that a former president, William Carlson, had been very active in polar research before he was recruited to lead this university in 1946. So we realized right away that we had a very good trade name for the series. But as it turns out, we also have a rich history of research and teaching in and about the polar regions, beyond anything that I ever could have imagined. We knew that President Carlson had implemented the university's first doctoral program in the late 1940s, and that he had chosen to create an emphasis on graduate education by creating a graduate course, actually a seminar, that was called Problems of Polar Research. The course appeared in the newly formed geography curriculum, which Carlson implemented. Well, okay. That sets the stage for what I just found out very recently. Many of you will remember the wonderful talk, the flyer for which is shown on the screen here, that was given in late February by Dr. Stuart Nelson. The topic was the intrepid explorer, Sir Hubert Wilkins, who in 1927 was the first to fly an airplane across the Arctic basin, crossing over the pole, an accomplishment for which he was knighted by the King of England. Stu Nelson's talk was about Sir Hubert's subsequent attempt in 1931 to take a surplus World War I submarine named Nautilus, after Jules Verne's underwater machine, under the ice to the North Pole. The expedition failed, but it made a wonderful story, and everyone who was at Stu Nelson's talk thought it was absolutely wonderful. Well, a few days after the talk, I received an email from somebody with a peculiar email address, USAAF43BG. But I knew immediately that that stood for U.S. Army Air Force's 43rd Bomb Group. The reason I knew that is because Bill Carlson was a colonel in the U.S. Army Air Forces during World War II and formulated some very important military strategy in the Arctic for that organization. But that's for another time. The gentleman who was writing to me, Mr. Alex Wysocki, asked if I knew that the last surviving crewman on the 1931 Nautilus expedition is alive and residing in no other city than Newark, Delaware. Holy moly. Well, of course I didn't know that. What an extraordinary coincidence. But it gets even better. Alex and Stu and myself have been corresponding over the past month and a half. And of course, you see the picture here in the lower left of Ray Dracchio in 1931. He's now 97 years old, and there he is holding a picture, holding a copy of Stu Nelson's book. Well, Alex managed to find out that Sir Hubert had lectured at our university in July of 1955. And figuring that the event must have been publicized somehow, I asked Ian Jansen and Lisa Gensel of the UD archives if they could find any announcement about the lecture in their files. Yesterday, we discovered that not only had Wilkins lectured about the Nautilus expedition on that July evening 53 years ago, he also had two former crewmen, one of them, Ray Dracchio, on the stage with him. But the real shock for me came when I read another of the press releases from the UD Office of Public Relations that year, announcing that Sir Hubert was a visiting professor of geography at UD that summer, and that one of the courses he was teaching, Problems in Polar Research, was the very course developed and put on the books 6 years earlier by President Carlson. To add to all of this surreal coincidence, Our partner organization in the Carlson series, the American Geographical Society, was a primary sponsor of most of Wilkins' expeditions, including the Nautilus expedition. So from all of this, it's very clear that the University of Delaware has a polar pedigree and that it dates back quite a while. So, okay, back to the present. Support from the university's colleges is really critical to this enterprise, not just because it provided much of the funding for the series, but because the colleges are the university's fundamental organizational units. Support from the colleges allows us to stitch the Carlson IPY events together in such a way that it makes them truly a university-wide enterprise. Before we invite Dr. Abdalati to the lectern, it's my distinct honor and privilege to introduce Dr. Tom Apple, Dean of the university's College of Arts and Sciences. Because of the topics involved in this evening's lecture, and you'll soon see the connections, CAS is sponsoring this particular Carlson public lecture. We're extremely grateful for the support and especially for the enthusiasm that it represents. Tom?
Well, thank you, Fritz, for asking me to be part of this really exciting and prestigious series. It's been a wildly successful program, and I think the evidence for that was the number of people who were in Thompson on that, who braved that ice storm in February to kick the series off. Also, as you've probably already noticed, following Fritz at the podium is kind of like batting after Ryan Howard. You know, so they intentionally walk Fritz to pitch to me. This series is made possible by a really unique cooperation, and Fritz was one of the driving engines of that, and I want to really thank him for that. We have the cooperation, as Fritz showed you, of an enormous number of organizations, and the College of Arts and Sciences is really proud to also take part in this and to partner also with the American Geographical Society of New York City as well. The public's recognition of changes in polar ice is really a rather recent phenomenon. And films and television specials, scholarly articles, and other media have contributed to this new awareness. Images of polar bears and penguins really help to put a face on this and the effect it has on the effect of the loss of ice cover. This evening, we'll actually celebrate both Ice Sheet Day, which was in, I hate when that happens, Ice Sheet Day, which was in December, and Changing Earth Day, which occurred in March. I will say that I'm very happy that today the university moves strongly towards green initiatives. You'll hear in the media today that President Harker held a press conference today to undertake a study of our own carbon footprint at the university. And we recently had our strategic planning committee present a report to President Harker. And that report has one of the three major goals to make this a sustainable university and also to study, as a university should, sustainability and green initiatives. So our three catchwords for our new plan going forward are graduate, global, and green. And I'm very proud of that. It's appropriate that the College of Arts and Sciences should be the sponsor of tonight's Carlson lecture. Our college has a long history, as Fritz mentioned, in work on polar ice sheets, on glaciers, and sea ice, going back to President Carlson. What you see here is actually, he spent many years studying the glaciers and climate in Greenland, and this is a satellite image of Greenland. But the College of Arts and Sciences is home to many faculty whose research and writings involve the polar areas. I'm going to give you a very small run through that here tonight before we listen to our speaker. Great. We'll start with Professor Martin Pomerantz. He's in the insert in the upper right. He headed the Bartol Research Institute, from 1959 until 1986. Professor Pomerantz was one of the first scientists to use Antarctica for astronomical and astrophysical observations. He carried the National Geographic Society's flag to the North Pole, to the South Pole in the late 1950s. The Pomerantz Observatory that you see here at the South Pole is named for him. His research in Antarctica continues today through the Bartol Research Institute, now within the Department of Physics and Astronomy here at the University of Delaware. The Pomerantz Chair of Physics and Astronomy was established through a generous gift from Professor Pomerantz and his wife in 1999. The Bartol work continues apace in both polar regions. The inset here shows left to right Stoyan Stoyanov, Tom Gaser, and James Roth from the Department of Physics and Astronomy at the South Pole on a recent trip. We actually received a blog during this trip on U Daily, and so we found out the recent happenings at the South Pole as they were conducting their experiments. By the time I'm done with this talk, I'll have figured out that you press the down arrow. Project IceCube is one of several major projects run by the Bartol Group. IceCube is a neutrino observatory for astrophysicists being installed at the South Pole over a period of 6 years. And its completion date is due in 2011. It uses an array of optical modules deployed in 70 vertical strings to depths of 2,450 meters in the Antarctic ice. This is an international project involving several countries. The U.S. National Science Foundation provides the major support for the design, components, drilling, testing, and maintenance of the equipment. The Department of Geography has a very long history of polar research. Starting with Professor Carlson. He suggested that a curriculum in geography be developed to meet the post-war needs for students to be well-versed in international affairs. And that was an incredibly insightful view to have at that time. By 1950, the program was in place. One of the first things President Carlson did after implementing UD's first doctoral programs in chemistry and chemical engineering, something I'm pretty grateful for since I'm a graduate of our PhD program here in chemistry, was to start an interdisciplinary research seminar. And the first speaker was Professor Carlson. The topic, problems of polar research. Throughout the 1950s and 1960s, UD geographers were active in Alaska. Joe Sonnenfeld studied Inuit culture and artifacts near Barrow, the northernmost settlement in the United States. Russ Mather, who's really the father of the geography program here and founder of the UD graduate programs in geography, also worked in Barrow on problems in climatology. And as you can see, work continues in the department on a number of and variety of polar and cryospheric topics. Kathleen Geiger in the department and Chandra Kambramethu from the Department of Computer and Information Sciences are co-investigators on a project funded primarily by the NSF Office of Polar Programs. This is titled Sea Ice Experiment, Dynamic Nature of the Arctic, or SEDNA. Other investigators in the project are from the University of Alaska Fairbanks. UD alumna Jacqueline Richter Meng of the U.S. Army Corps of Engineers is also involved in the project. The research team's main objective is to better understand the interaction between the atmosphere, the ocean, and sea ice cover, and the influence of those factors on the mass balance of ice cover, using field studies, remote sensing, and modeling. The results are being used to improve models of sea ice cover, leading to better predictions of future changes and impacts on regional and global communities. The UD Permafrost Group is involved in projects in Alaska, Russia, Tibet, Mongolia, and Peru. They also have several projects operating in the Mid-Atlantic and the Appalachian regions investigating the effects of permafrost during late glacial times. The group operates the Circumpolar Active Layer Monitoring Program, known in shorthand as CALM. CALM is an international global change monitoring program focused on observing the dynamics of the seasonally thawed layer and permafrost regions and changes in the upper layers of regions and upper layers of permafrost. The program currently encompasses 168 observatories in both polar regions and several more in mid-latitude mountain ranges. This slide shows the location of CALM observatories in the Arctic region. Scientists from 15 countries are involved in the CALM program, which is administered here at the University of Delaware by Fritz and Nikolay Shiklemanov in the Department of Geography. The network is funded by NSF and has formal status as an International Polar Year project. Our work in the polar regions also extends into the social sciences and the arts and humanities. College of Arts and Sciences faculty have been active in UD's study abroad program, including trips to Antarctica in 2004-2005. Ralph Begleiter, a former CNN international correspondent many of you know from our international series, in the Department of Communication, worked with John Cox from the College of Agriculture and Natural Resources, and their trip focused on geopolitical issues involving Antarctica and surrounding regions and journalism and photography. As I mentioned earlier, the College of Arts and Sciences' involvement in polar affairs are wide-ranging. McKay Jenkins, who you see here at on the right-hand side at the top, in the Department of English, has written several books involving polar or cold regions. One of his most recent is Bloody Falls of the Copper Mine, which is a story about the ill-fated trip of two hopelessly unprepared Catholic missionary priests in Arctic Canada and the Royal Northwest Canadian Mounted Police investigation into their killing at a time when the region was virtually unexplored by non-native Canadians. The resulting collision of cultures involved in an epic 3,000-mile investigative journey and culminated with the trials of two Inuit men in southern Canada. McKay and his brother spent many, many months in northern Canada researching the book. Our world-renowned Center for Material Culture Studies, under the direction of Dr. Debbie Andrews, who also holds an appointment in the Department of English, has been very active in the Carlson International Polar Year Project, and they maintain a strong interest in the cold regions. The quote that comes to mind from Dr. Andrews is that the center has interests in objects on ice. In other words, the cold lands and the forms of ice that shape the lives of people in polar regions and the objects and images that people make that allow them to live there. These are points of interest for many faculty affiliated with the Center of Material Culture Studies and their students. And that leads me to a further point. The University of Delaware's resources and talents in the arts are very strong. And as many of you know, our collections of polar art and material culture are also very strong. Janice Tomlinson will make a major announcement about polar art and the Carlson series in just a minute or two. And even I don't know what it's about, so I'm very excited. Finally, it's important to keep in mind that one of the university's primary functions is to create and disseminate knowledge. One of the very important ways in which we fulfill this mission is by preparing our graduate students for roles in university-level teaching and research careers. People who have trained or participated in research in polar topics here at the University of Delaware are engaged in creation and dissemination of knowledge about the polar world at many institutions of higher education in the United States and in other countries, including work done including Canada, the United Kingdom, Norway, Russia, and New Zealand. It's clear that the work done in our college and elsewhere in the university is becoming increasingly well-known and influential in the polar world. I join you in looking forward to the fantastic Carlson lecture, and I thank you for your attention.
Thanks very much, Tom. I think that Tom's overview of the CAS mission and the units in the college underscores a very important fact. The fourth International Polar Year is not just about science. It's also about the whole range of human endeavor, including engineering, social science, education, and the arts. So in that vein, Dr. Janice Tomlinson, Director of the University of Delaware Museums, is here to make a very special announcement that I think will be of considerable interest to this audience. Thanks, Janice.
After that build-up, I really hope I don't disappoint. First of all, everyone says what museum, what the university museums are, is really three different galleries with collections, so yes, they can be called museums. One is University Gallery in Old College, I hope many of you have been to. The other is the Paul Jones Collection in the building of Mechanical Hall, and the third is the Mineralogical Collection in Penny Hall, which is now closed for renovation. The University Museums really is delighted to present two exhibitions this coming fall in conjunction and partnership with the Carlson International Polar Year. Together, they will present images of exploration ranging from 1869 to the present day. Those from 1869, one of which is now on the screen, document the voyage of the SS Panther, which was chartered by a painter. Two professional photographers were also on the expedition, and their works were published in two books that were widely disseminated in the U.S. in the 1870s. The historical photographs, so seen here and there, come to us from the American Geographical Society Library in Milwaukee. They were featured in an exhibition last fall entitled Photographs from the Ends of the Earth, and we borrowed that title, presented at the Milwaukee Art Museum. The curator of that exhibition has been very generous in helping us plan our exhibition. And I do want to thank Fritz Nelson for bringing this exhibition to my attention. And Fritz is also working on adding some selections to the historical photographs to be seen. Included among those will be this image of the transatlantic submarine expedition of 1931, the Wilkins expedition, which was the subject of the lecture to which Fritz referred. As many of you may know, this exhibition, although it was a failure, attempted to go under the ice of the North Pole in a refitted World War I submarine. They crossed the Atlantic from New York to Ireland before going to Bergen, Norway, and to Spitsbergen, where they attempted to dive under the ice. This photograph documents where they were before, just the Spitsbergen, phase of the expedition right before the attempted dive. Looking from past to present, the second exhibition, and they will both be in Old College in two adjacent galleries, the second exhibition will present the work of a contemporary photographer, a very young photographer named Camille Seaman. Seaman was inspired by her first sighting of an iceberg only in 2005 and does not come from a scientific but rather from an artistic background, and subsequently traveled to the Arctic regions of Greenland as well as to Antarctica, photographing, sort of creating majestic photographs of the icebergs that she saw. That now on the screen depicts the Grand Pinnacle iceberg in East Greenland. The lower image depicts icebergs near Franklin Island in Antarctica. These are digital digital inkjet prints, some of which are 93 inches long. I mean, they're really quite incredible. Another two images of Seaman's work from icebergs in Antarctica. Listen, I hope you'll all join us for the exhibitions. If you haven't heard about the museums, and if you'd like to be on the list so you get information not only about the exhibitions, which will open on September 9th, but also about the programs that Fritz and I are planning to go along with them, please just send your contact information to universitymuseums@udel.edu. If you don't want to be put on our mailing list, although I do hope you do, you can just say just the Polar exhibition, but I hope you'll come back. Thank you very much.
Thanks very much, Janice. And while I'm thinking of it, I guess in the vein of better late than never, I had so much trouble with the computer here that we ran this little audio clip beforehand that said, don't do this, don't do that. I've been informed that it's absolutely fine to use, as some of you have been, flashes and to take cameras during these proceedings. So, better late than never. Our speaker tonight is a man of great knowledge and great accomplishment. And it is indeed appropriate for Dr. Waleed Abdalati to be delivering one of the W.S. Carlson IPY public lectures at this time. The IPY's International Program Office in Cambridge, England, has organized events in the 4th International Polar Year around a series of International Polar Days, which are scheduled to coincide in a very general way with the solstices and the equinoxes. The Carlson Committee has undertaken to follow the sequence of these polar days, although we can't replicate the actual timing because the Carlson series didn't begin until early 2008. At any rate, Lawson Brigham's talk in February brought us on board with Sea Ice Day. A little bit behind, but again, better late than never. Tonight's speaker brings us up to date because the topic of his lecture covers both Ice Sheet Day and Changing Earth Day. So, as of tonight, we're on track and up to date with the main IPY events worldwide. Waleed Abdalati is known widely as an engaging and dynamic speaker, and he's also known for his use of extremely impressive graphics to illustrate his points. So before we bring him on, let me tell you a little bit about him and his accomplishments. Waleed holds a doctorate from the University of Colorado. Before he joined NASA 11 years ago, he was an engineer in the aerospace industry. Throughout his career, Dr. Abdalati has exercised what I think is an admirable combination of field investigation and laboratory work, primarily in the area of remote sensing. He's been on 9 field expeditions to remote areas in Greenland and the Canadian Arctic. From 2000 to 2004, he managed NASA's Cryospheric Sciences program, which involved work on glaciers, ice sheets, sea ice, and polar climatology. For the last 4 years, he's been head of the NASA Goddard Space Flight Center's Cryospheric Sciences branch, a group of scientists that works with satellites and aircraft instruments to understand the Earth's changing ice cover. He's also been involved in developing, that engineering background here, satellite-borne instruments specifically designed to observe changes in ice in the polar regions. Dr. Abdalati has received a substantial number of major awards, including the NASA Exceptional Service Medal and the Presidential Early Career Award for Scientists and Engineers from the White House. The title of Dr. Abdalati's lecture tonight is Dramatic Changes in Earth's Polar Ice. Are we waking sleeping giants? Waleed, we'll have to take just about a half a minute to change computers here, and then we'll be on the road. Anything I can do?
Hold on. Yeah. This that it won't advance all by itself, but we'll see. Can I close this? All right. Okay, well, let me start by telling you my name's Waleed Abdalati, as Fritz said, and I work at NASA. And I'm going to talk to you about changes on ice, a little bit about NASA, a little bit about ice, and a lot about changes. Let's see, I like to start this, first of all, by thanking the University of Delaware for the opportunity. I think it's very important that institutions like this create such opportunities for you to learn, for me to talk, because I like to talk, but more importantly, for you to learn. And there are a number of acknowledgments I didn't put on a chart, but certainly NASA for the great opportunities it's provided for me to really understand and explore the polar regions, the scientific community, because what I'm going to show you is the product really of the work of many, many scientists. But most of all, I want to acknowledge you, because it's when people come and hear this stuff, people come and try and learn what's going on, that we can start to make a difference, that the value of the science is really realized. So, of all the acknowledgments, I think my biggest debt of gratitude goes to you for your time and attention. So I appreciate that very much. Now, like I said, I'll leave it here. Not only does it not advance by itself, it doesn't advance when I do it. Okay. I work for NASA. Although I need to say that the opinions I offer tonight are my own. They don't reflect those of the agency necessarily. They do reflect those of me, however. And when I tell people I work for NASA and I study the Earth, I get kind of a puzzled look, because when people think of NASA, they think of the moon. They think of the Hubble Space Telescope. You know, and I first became hugely enamored with NASA, as most people in my generation did, when I was a kid and I watched the lunar landings. And I remember, you know, Neil Armstrong, one small step for man, et cetera, Buzz Aldrin right behind him, and even Michael Collins, who a lot of people forget about, orbiting alone in the module, in the capsule about the moon. And I fell in love with NASA. I wanted to be an astronaut. Most of you probably did too, who were my age at the time. And in my mind, I was an astronaut. I mean, I was an explorer, and my best friend Matt Perry and I used to go out on his swing, and we'd swing as high as we could. You've all done it, you know, as a kid, you get higher and higher, and then you just sort of let yourself fly through the air and you land, right? And we landed on the moon, and we were exploring the moon in Matt Perry's backyard. Now, it was his swing set, so he always got to be Neil Armstrong. But I got to be Buzz Aldrin, which was cool. I liked that. And occasionally there was a third kid that wanted to come play with us. We let him be Michael Collins, but he was never allowed to jump off the swing. So we would walk around, explore, come back, all drink some Tang, and we'd tell him the kinds of things we saw while we were out there. But eventually NASA showed me something that changed my perspective of the agency and of the world. And it was a picture like this. You've all seen these kinds of pictures from Apollo 17, where astronauts had the brilliant idea of looking behind them and taking some pictures. Changed the way we looked at the world. And as a kid, to me, this prompted hundreds of questions. Why is some of it blue? Why is some of it white? Why is some of it green? How come the clouds look like they do? How come you can see through some of the clouds and not the other ones? Where were the clouds yesterday? Where will they be tomorrow? Why do they move like that? I was so annoying to my parents, but I asked these questions, and I was inspired. So I'm going to talk to you tonight about the polar regions. All you see up here is the North Polar ice cap. And as I do, or before I do, I kind of want to set the stage. And this is kind of risky when you give an evening talk, but I'm going to invite you all to close your eyes for just a minute. Not even a minute, but just close your eyes, keep them closed, and imagine the coldest you've ever been. Feel the goosebumps, feel the chills, and now turn it down 20 degrees. I don't want to see any open eyes. Even if you don't do this exercise, keep your eyes closed. I'll wake you up when it's over. Turn it down 20 degrees and really feel now the sting, okay? Turn up the wind about 20 miles an hour. And the burn on your face or any exposed skin. Make it another 10 degrees colder, and turn up the wind another 10 miles an hour, and make it dark, and make it light. And open your eyes. And there are places on Earth that are like this all the time. And these places play a huge role in shaping our planetary environment, and these places have certain characteristics. They're pristine. This is from the Antarctic Peninsula, untouched by human feet, this particular location. We were flying over it in a low-flying aircraft. They're rugged, they're raw, they're nature in its most austere form. They're huge. Ice, hundreds of miles, thousands of miles in any direction. This was home for about a month. These are sleeping tents, kitchen tent, work tent. This guy snored. You can notice the space. This was my tent, actually. And that guy snored, and if you saw the picture 2 weeks later, you wouldn't even see the edge of the tent. He'd be more to the side. Huge places. They're humbling. You cannot go to a place like this and not be humbled by it. Feel very small. They're beautiful. Really unlike any place you'll ever see on Earth. The way light interacts with the ice, the filtering of the blue lights by the atmosphere through these long atmospheric paths that the light has to travel through. And they're changing. This is the calving front of the Jakobshavn ice stream. You're going to hear me talk a lot about the Jakobshavn ice stream, but what is a calving front? Well, the glacier is up here, flows down this way, where the icebergs break off into the sea. This is a fjord, and they flow out to the ocean. Okay? This is a close-up. I took this picture in 1993. These places are changing. The helicopter I was in when I took this picture was about the size of the dot that the laser pointer is illuminating. Imagine these things as tall as a football field is long. Just 50 yards of ice above you, 50 yards of ice below you, and you're in this little tiny helicopter. There are a lot of stories that go with that I don't have the time to tell, but I think you get the point. These are big structures, and they're changing. Well, so what? Okay, this ice is doing strange things that I'll talk about in a little bit. Does it matter that a place none of you will probably ever go to? I hope you do if you ever get the chance, but does it matter that a place like that is changing? Well, it turns out it does, and it does for a lot of reasons. Okay, this is a depiction of the Arctic ice cap, the Arctic sea ice, the Greenland Ice Sheet. You can see the glaciers on the Canadian archipelago. It matters for several reasons. One, the Arctic sea ice it's a thin veneer of frozen ocean surface water, and it provides a barrier between the ocean and the atmosphere, trapping heat in the ocean in the wintertime, preventing the evaporation or the moisture entering the atmosphere in the springtime, exchanging salt with the ocean below it. And climate as we know it has come to sort of count on or depend on this ice being here. The global ocean circulation patterns are rooted in the polar regions. Nearly all the water at the bottom of the world's oceans originated in Antarctica. The next layer up largely originated in the Arctic. It's sort of creeping around the bottom of the oceans. But it matters because it affects climate and weather worldwide. It also matters for sea level. The Greenland Ice Sheet holds the equivalent of about 23 feet of sea level if it were all to disappear. 23 feet. It's not all going to go tomorrow. It's not all going to go in the next couple hundred years. But what does matter is how much of it may disappear. These are the sleeping giants I'm talking about. How much of it may disappear, contribute to sea level rise in the next 50 years, in the next 100 years. Sea level rise matters because most of the world's populations are concentrated in low-lying coastal regions. But even if you're not low-lying, there is the little problem of erosion. You can be high up, but with the ocean lapping at the land's edge, there's potential for disaster. The land also serves as a barrier to weaken storms or weaken the effects of storm surges. As that starts to get inundated or submerged, those effects become worse. Sea level matters. 23 feet in Greenland, almost about 9 times as much in Antarctica. This is a picture, an illustration of the most vulnerable part of the United States to sea level rise. White is the populated areas. I tried to get Delaware last night, but then the software crashed. It's kind of like this Vista that you guys were using, and just when you need it most, it's not there for you. But these are the areas affected by a 1-meter sea level rise, 3 feet. That is not really unreasonable for the coming century. We don't know that that's going to happen, but it's kind of at the upper end of the bound that we think may be coming. Huge implications for coastal U.S., huge implications all over the world. These are areas affected by a 3-foot rise in sea level all over the world. Now, in the United States, at least we've got money, we can move. You start to get to areas like Bangladesh, much more densely populated in coastal regions and far fewer resources to deal with sea level change. It doesn't only become a physical problem, the loss of land. It becomes a social problem, a societal problem. You don't have to pay too much attention to these graphs. It's more these numbers, okay? The land area that would be removed by a 1-meter rise in sea level is 2.2 million square kilometers. That's about a quarter of the area of the continental U.S. About 145 million people affected, either, displaced, let's just say adversely affected by a rise in sea level. Close to $1 trillion in cost, a 1-meter rise in sea level. These are all things that really matter. And the $1 trillion is, to me, that's material cost. I don't think you can put a price on this. What happens there matters here. And finally, this is the most sensitive aspect of the climate system, the polar regions, because of what we call the positive albedo feedback. Ice is white, it reflects sunlight. As it starts to melt, it exposes a darker ocean underneath, which absorbs sunlight, which makes it get warm, which causes the ice to melt, which exposes more ocean, which absorbs more sunlight. I think you see where this is going. It's self-compounding. There's nothing to stop it once it starts. But fortunately, nature does a wonderful thing every year. It pushes a reset button, and winter comes, and the ice freezes over, and we start the cycle again. But it's not quite that straightforward. I love this picture for a lot of reasons. You probably figured out those are graduate students there. But I love this picture because it says to me all that's challenging about doing research in polar regions. And when I tell that to people, they say, yeah, I see that. Looks cold, looks dangerous, looks hard to get to. That's all true, but that's not what I see. Scientifically, it shows me the challenges of scale, of perspective, of context. How do you turn a measurement there into something meaningful about an entire continent? Those guys, friends of mine, were just a little speck, much, much, much smaller than the dot you see on the screen. Right here. Critical work they were doing, but how do you relate what happens here to the rest of the continent? Okay, these are temperatures in Antarctica. A lot of the Antarctic continent has been cooling until recently, and I can talk more about that later. But the edges have been getting warm in a lot of places. Context, scale, and perspective. Now I come back to NASA. Okay, this is where the satellite view has really done tremendous things. I'm going to get to that. Let's talk now. This is your Ice Sheets 101, how an ice sheet works, okay? Because you need to understand this. An ice sheet grows when snow falls and not all of it melts. And then next year, more snow falls and not all of it melts. And eventually it accumulates, compresses under its own weight, starts to spread to the edges. So these ice sheets grow in the middle as snow falls. When it spreads to the edges, they either break off as icebergs into the sea, or at the lower altitudes, they melt and the meltwater runs off. In a warming climate, all of these processes increase. So we lose more ice at the edges, but we actually gain more in the middle. The question is, what's winning? What's the dominant effect? This is the Antarctic Ice Sheet. I'll jump ahead. The losses are the dominant effect, and you'll see why. This is the Antarctic Ice Sheet. We have ways of observing the flow of ice to the sea, the melt that occurs in the peninsula, the accumulation in the interior, the calving of icebergs at the edges, the movement of the sea ice, the thickness of the sea ice to some extent, the area of the sea. We can do all this from space. We got to get up close and look at it in detail, but in the macro scale, what we call a macroscope, we can look at all of these processes. Antarctica holds the equivalent of over 200 feet of sea level rise. Temperature's well below freezing, so it doesn't melt much. And the West Antarctic Ice Sheet, this area in here, is about 5 meters or about 16 feet of sea level equivalent. This is Antarctica without ice. It's not red, really. It's just a depiction. But the blue shows areas that are below sea level. Well, this turns out to be tremendously important because as this ice starts to retreat in the area we call the weak underbelly, there's nothing to stop the water from coming underneath and eroding it and causing that retreat to go all the way inward. This ice, this big slab, sits on a soft bed till, we call it. You've all experienced it if you've stepped in a swamp. You know, that mucky, slippery, muddy stuff at the bottom. So it's not, frozen to bedrock. Very vulnerable, and hence called the weak underbelly. Well, what would a collapse of the West Antarctic Ice Sheet look like? Well, the weak underbelly, the calving front would start to retreat, move inward. The glaciers would start to accelerate. The ice would get thinner and thinner as it was flowing out to the sea. We're seeing all of that from space. Now, that does not necessarily mean catastrophic collapse is underway, but the observations are consistent with that. And by catastrophic, I need to clarify. Catastrophic in glaciological terms means a few hundred years. It doesn't mean, boom, all of a sudden you have to run to the hills. But a few hundred years at 5 meters is catastrophic. I'm going to take you now to the Antarctic Peninsula, one of the most rapidly warming places on Earth. A lot of Antarctica is cooling. The peninsula sticks out outside of the cooling region and is actually warming quite a bit. In 2002, this was on the front page of the New York Times, we saw something that we as glaciologists really couldn't believe. This area here, the Larsen B ice shelf, is about the size of the state of Rhode Island. And for reasons I can't figure out, the standard unit of measure for icebergs seems to be small New England states. Occasionally you'll get a Delaware in there, but it's rare. But I'm going to take you through this. So about 2,200 square kilometers, about 700 feet thick. I'm sorry, I'm switching units on you, but it's just how I know it. About 700 feet thick and about 10,000 years old. January 31st, a few days later, about a month later, a few days after that, and about a week after that. Let me take you through that again. 10,000 years of ice gone in a month. We didn't know ice could do that until we watched. Turns out it can. But the removal of this ice in and of itself doesn't really affect sea level because it's been floating. Okay? It's already displaced the water it's going to displace, and just because it melts doesn't change sea level. But what happened after that was these glaciers all accelerated. This one in particular, the Crane Glacier, flushed its ice out into the sea. Its speed went up 8-fold because this buttress, this barrier to flow was removed, and all of a sudden the ice could flush out. That hasn't been sustained. It's now going, this was in 2002, it's now going about double its earlier speed. But it speaks to the buttressing effect of this ice, and as it becomes more vulnerable in a warming climate, the potential for discharge increases tremendously. These glaciers didn't change at all. They still continue to be buttressed, which suggests it's not a climatological phenomenon, but really a structural one based on the removal of the ice. Now I'm going to take you to Greenland, the other ice sheet, as I like to call it. I already told you how much sea level is stored in there. Greenland's a little different because a lot of it melts. The area here in pink and red are areas that experience some level of melt, a nominal level of melt on the surface in the summertime. Okay? Well, let's zoom in to the Greenland ice sheet. We're going to come into the Jakobshavn ice stream, which I mentioned in the beginning. But it's going to pause, and you're going to see these blue lakes. These are melt lakes. Okay? There are undulations in the surface of the ice sheet that the water accumulates in. Okay, these blue dots are all melt lakes. I'm going to talk a little more about that. But because there's topography on the ice and running water at the surface, runs along the ice surface, these lakes accumulate and they form. We're going to zoom in now to the main ice stream. And what you see here is the calving front, actually here now, the calving front, the icebergs that flow to the sea. This is the main ice stream with the fast flow with long vectors, the tributary, and what we call drawdown, ice that gets sucked in or entrained in the main flow. Okay, this is one of the fastest glaciers in the world, about 7 kilometers a year. And in about 2000, 2001, this calving front began to retreat, about a mile a year. This ice is floating, this is on land, this is icebergs that get carried, so this is a broken up version of this, carried out to the sea. So that in 5 years, the ice retreated 5 miles, which is the equivalent of the previous century. Okay, this was a stable front for about 50 years, and then it just started retreating very rapidly. And it turns out, as was the case with the Larsen B ice shelf, when that happened, the glacier, one of the fastest in the world, and I got to find my little, there it is, one of the fastest in the world, doubled its speed to 14 kilometers a year. That's 5 feet an hour, which means, I mean, for a glacier, that's just almost unheard of. That means you can actually stand there and watch it move through your field of view or your line of sight. If you line up with a rock, you can see the ice move. That alone is worth the trip. But what happened subsequently, so this ice accelerated its flow, flushed its ice out to the sea, and this is elevation information you're looking at now. Purples are sinking of the ice. Remember that entrainment, those little flow vectors? As that ice speeds up, it takes the reservoir with it. So this is starting to slump. Well, it turns out it's not only here, it's all along southeast Greenland. This ice, these buttresses to flow, are starting to diminish, weaken their restraining effects, and the ice is spilling out into the ocean. Same up here, and it seems to be creeping northward. A friend of mine likens it to a tube of toothpaste that's got dry toothpaste caked on it, and you squeeze it and little comes out. You clean off the toothpaste, squeeze it again with the same force, a lot more toothpaste comes out. An ice toothpaste analogy or whatever, but I think you get the idea. Remove the barrier, and it can flow. And that's happening all over Greenland, which makes us wonder what it's going to do in the future as the climate warms. This is just fun to watch. This is the Jakobshavn ice stream, the calving front, the ice stream up here, a different view. Remember now, this is about the size of a football field, a little bigger. This is about the size of a city block. And this is just a movie that Jason Amundsen from the University of Alaska happened to catch. That whole slab spilling into the sea, turning over. Keep in mind, the size of a football field, but it's 10 times as thick in actuality, because 9/10 of it is below the water. Tremendous. And this is happening a lot, and the ice is marching its way backwards before it can be replenished by the flow of ice. All right. This is an area of the bottom of the ice sheet, the bedrock, and the blues show areas below sea level. Okay? You can see that in Jakobshavn, we have this little stream, this little trickle. This is huge because it's the gateway to all of this ice, the thick stuff in the interior. So as it starts to erode, we aren't sure what's going to happen, if there's going to be this significant drainage from the interior. We use ice-penetrating radar to look through the ice. This is what the channel looks like if you were to remove the ice. And again, it's not colored. I don't think it's red at the bottom of the channel, but you get the idea. The water can sort of penetrate in here, keep eroding at that ice, all the way back potentially to the interior of the ice sheet. I mentioned melt and melt lakes. One of the things I did in graduate school when I wasn't on the ice was I figured out a way to figure out how much ice is melting from space. Using satellites back to 1979, I've just sort of kept it going. Old habits die hard. And we see about a 30% increase in the amount of melt on the Greenland ice sheet. Well, what happens to that water? Well, it accumulates in these lakes, like I told you. Some of them, they tend to be, 10, 20, 30 feet deep, a couple miles wide. They vary. Hundreds of them on the ice sheet. This is what they look like from an airplane. Some of them. This is a nicely defined lake. Well, that water finds a way, either through tunnels or through crevasses by prying them open under their own weight. It finds a way to the bottom. This is actually the most famous picture in glaciology. This was in Business Week and Time Magazine, the Journal of Glaciology, which I'm sure all of you read. One of these guys is my glaciology professor, and I haven't asked him yet which one is him, but I'm pretty sure it's the one farthest away from the flowing river. And again, back to the grad students. When you're not in the southern hemisphere, you're in the northern hemisphere. This is what the water looks like going down through about 1 kilometer of ice, maybe half a kilometer, half a mile, we'll say. So it flows along these rivers, burrows into the ice, and eventually it carves away so much ice it becomes really a flowing river rather than a stream. Well, this is an animation that shows what happens and why it's significant. Okay, we're going to zoom into the melt lake, the water in the topographic basin. When enough head pressure builds up, the water finds a way through the ice to the bottom where it flows along the interface between the ice and the bedrock, makes it slippery, and the ice speeds up. The ice in some cases goes twice as fast in the summer as it does in the winter. The more it melts, the faster it goes. So this melting is kind of a double whammy. There's the loss of ice directly from the melt, and then there's the enhanced discharge, the accelerated flow, as a result of that meltwater reaching the bottom. Well, we have a lot of tools for studying ice, and one I've worked most extensively with is ICESat, the Ice Cloud and Land Elevation Satellite. Satellite flies along, fires a laser at the surface, measures the travel time of the laser pulse, and from that we can figure out the elevation of the surface. We build those up over time, and we start to get the topography of the surface, and over more time, how that topography changes. We see where the ice is growing, where the ice is shrinking, and from this information we can figure out how much the ice is contributing to sea level, but also the mechanisms, because the nature of that topographic change holds clues as to what's causing it. Okay? We're used to pictures, we're used to digital images from space, like the Larsen B ice shelf collapse. Hugely valuable, but there's that other dimension that's tremendously important for figuring out what's going on. Almost said what's going wrong. And it's that topographic data that has shown us this slumping in parts of the ice sheet, but a little bit of growing as more snow has fallen in large areas of the interior. Another mission we have, which I think is really cool, it's called GRACE, Gravity Recovery and Climate Experiment. And it works like this. 2 satellites fly along. Let's pretend this is an ice sheet. Okay? They fly along and they fly over a big mass, in this case an ice sheet or a microphone. The orbital velocity of the satellite depends on the mass below it, or the gravity below it. So the first one speeds up when it hits this, increasing the distance between the two, till the second one gets there and it speeds up. So the distance here is the same as the distance here. But by measuring that separation, we can figure out the weight of the ice underneath, or how much that's changing over time. We've applied this to Alaska. A couple guys I work with, Scott Lufke and Anthony Arendt, Anthony's from the University of Alaska, have done this. And we see how much ice is disappearing from the Alaskan glaciers. This is the equivalent of about 0.3 of a millimeter of sea level rise. Sea level rise is it's only going up a little bit. Okay, it's going up about 3.5 millimeters a year. That's not much until you stack it up over time, until you stop and think that 50 years ago, it was going up at half that speed. 6,000 years ago, it was going at about a quarter of that speed. 10,000 years ago, it was going 30 times that speed. So there is evidence in our past of big changes in sea level as a result of ice. Well, this is where it's happening in Alaska. Greenland and Antarctica are exhibiting similar phenomena. Okay, end of ice sheets for the time being. I want to call your attention now to sea ice. Remember I said it's a thin veneer of frozen seawater. It's an important distinction. Ice sheets are freshwater ice. It's snow that falls and doesn't fully melt. Sea ice is frozen seawater, and when it freezes, it rejects salt. It drops brine or salt into the surface of the ocean below, which makes that cold water even more dense, which causes it to sink. Okay? Salty, cold water sinks. That's why it's along the bottom of the world's oceans. Well, if you've ever been in a swimming pool and you put your hand on the surface and you push down, what happens? Water comes in to fill the void where your hand was. Same happens in polar oceans. As this water sinks, water is drawn poleward from lower latitudes. This is all part of the global ocean conveyor belt. The circulation characteristics worldwide are coupled with sea ice. Plus, it's home to the polar bears and other creatures, which you hear a little about. Well, sea ice grows in the winter, shrinks in the summer, grows in the winter, shrinks in the summer. And remember I said nature pushes a reset button. Okay, it gets smaller and smaller to what we call the summer minimum, and then it starts to grow back. It's a wonderful thing, because if that didn't happen, that positive albedo feedback would kick in, and we would lose it. Okay? Now, if you look at the minimum, right now, okay, that tells us something about sort of the state of the Arctic climate, the health of the Arctic sea ice. And we can track this in time from 1979, from the early satellite records, to, right, this goes to 2005. And if you do it, your eye can pick up a shrinking, particularly in this area here. It's going to loop through again, so watch that. So it's sort of filled in here and filled in here in the early part of the record, but you can see it shrink at about 8% per decade. Okay, so that's a significant loss of sea ice. And in 2005, well, we'd been worried about it for quite some time, and in 2005, we were really alarmed. This is the early part of the record, the late part of the record. Okay? Early, late. We were struck by the trend that was punctuated by a very low sea ice year in 2005. And people started to speculate, well, when is this ice going to be gone? The models back then told us maybe the end of the century, and they didn't all agree on that. But in 2005, the models got better, and the sea ice got smaller, and that estimate was revised to maybe 50 years. But in 2007, we were really stunned even further. The ice reduced by 23% from 2005 to 2007. Huge amount. Again, like the Larsen B, we didn't know it could do this. This is the average. You'll see 2005 again, the previous minimum, where we were all saying, wow, that's small. And in 2007, much, much smaller. We don't use New England states for this. We actually use California, Texas, Alaska, those kinds of things, because it's bigger. But this area in here is about the size of the continental U.S. I wanted to pause it, but I missed it. Now, in here, actually, I'll run through it again, just for fun. I'm not sure it'll do it, but in here, this is the Northwest Passage, okay, from Greenland through the Canadian archipelago, and you can see, and then here through the Bering Strait out to the sea. You can see that in 2005, in the low melt year, it was filled in with ice. Okay? In 1905, Roald Amundsen traversed the Northwest Passage. He finished his traverse of the Northwest Passage. It took him 3 years, and it followed dozens of failed attempts, some very tragically. In 2007, a 76-year-old farmer from Minnesota did it in a sailboat in 73 days. Hardly the image of the intrepid Arctic explorer, you might. Well, unless you're a 76-year-old farmer, then it probably is. The point is, these areas are opening up. These areas are potentially opening up, and I'll speak to what that means a little bit later. This is a curve of the best model estimates of the disappearance of Arctic sea ice out to 2050. Okay? About 14 models go into the predictions of future climate. You run them for sea ice, and they give you a range that's bound by the blue of what's going to happen to the Arctic sea ice in the next 50 years, and you can kind of extrapolate sometime by the end of the century it'll be gone. Here's the problem. They're all wrong. They don't keep up with what the ice is really doing. Throw in 2007, where we're where we expect it to be in 2050, and it really makes us rethink our predictions. Okay? Maybe it's doing this. This year will tell. Well, it'll help tell. It takes more than a year to figure out what's going on. But the reason these models are not very good or don't quite capture it, it's not fair to say. These are models tuned to figure out the climate of the world. So to pick on one parameter and say they're not quite getting it right isn't really fair. But the fact that they're not getting the Arctic right and that it's such an important part of the global climate system does make us wonder, how conservative are these models? Well, remember ICESat fires laser pulses at the surface. We have a way of getting at that missing thickness information, and that's by measuring the difference in height between the water and the freeboard, the ice above the surface. We adjust for density, and we can estimate the sea ice thickness. And this is hard to read, I apologize for that, but these are sea ice thickness maps in the fall of 2003 through 2007, since the ICESat mission has been operating. And what you can see is that the really thick stuff here, actually, let's look at the 2-meter ice here, is gone. It's very thin. Okay, the really thick stuff, the 4-meter ice, the 3 to 4 meter ice, also disappearing. The ice is getting thinner. So even though nature pushes a reset button, it doesn't really reset it, because when this thick, old, hardy ice disappears, it's replaced by new ice, which is thinner and more vulnerable to melt. So the potential for rapid decline or melt in the summer tends to increase as this goes away. So what does an ice-free Arctic mean? Well, it means a lot of things. One, more heat is absorbed by the planet. Remember the movie. You get rid of the white ice cap, expose a dark surface, the Earth is going to absorb more energy. This can affect climate patterns worldwide. Throughout sort of recorded human history, we've counted on this ice being there. Change in wildlife habitat. You've all heard the stories, and it really is sad, but polar bears have to swim farther to their food, and eventually the ice starts to reach a point that's beyond the swim range of a polar bear. But that's not the only issue. It's not that they can't get food. As these polar bears get smaller, and they are getting smaller, they're starting to approach a weight at which they cannot reproduce. Mother Nature protects them. You don't have enough in you for offspring, use it for yourself. So their numbers are diminishing. Ironically, though, their sightings are increasing. And the reason for that is they're not finding the food at sea so much anymore. They're going into Churchill, Manitoba, into people's trash, and they're finding the food there. It's an interesting dynamic. There are some good things of an ice-free Arctic. Transpolar shipping routes. This is the Northwest Passage, so Greenland through here. So you can see, well, let me focus on the Northeast Passage. As this ice disappears, getting goods from Asia to Europe or goods from Asia to the eastern United States becomes a different issue. You no longer have to go through the Suez Canal. The travel routes are much shorter. This could potentially impact commerce substantially. It can also potentially impact national security, as we have what has historically been a closed border to North America start to open up. Adding to that, there are likely tremendous resources in the Arctic Ocean. Everybody's going to want a piece of that. Nations are already falling over themselves to plant flags. Okay? This is potentially huge. Huge economic implications, huge ecological implications, huge strategic implications, huge social implications. Other recent changes in the polar regions. Warming of high latitude surface temperatures. More than any other place on Earth, the Arctic as a whole and the Antarctic Peninsula are warming more rapidly than anywhere else on large scales. But a lot of the Antarctic surface is cooling. There's a whole interesting story between what the difference is between that. But that cooling of Antarctica is starting to change, but it makes you wonder what's different about the dynamics, and I can speak to that afterwards if anyone's interested. Melting permafrost. Okay? Frozen soil is thawing. It's as simple as that. When that happens, a few things happen. It releases methane into the atmosphere. Methane is a very strong greenhouse gas. This is another positive feedback. Permafrost thawing releases methane, more energy is absorbed, temperatures go up, more permafrost thaws, and so on. It also has practical implications. The state of Alaska, this figure is from 2000, spent $35 million a year on infrastructure repairs because buildings built on what used to be frozen soil are now having settling issues. Okay? Adjust that for inflation and more rapid thawing, and that number may be double now. Earlier melt onset of Arctic sea ice, earlier breakup of lake and river ice, snow is melting earlier. By the way, these are all freezing later. And we're seeing signs of changes in the ocean and atmospheric circulation. Subtle ones that are still being debated, but the hints are certainly there. Okay, in the remaining time, I want to take you now into the ice. Okay, I talked about how the ice is changing. Well, the ice also holds a remarkable, tremendously valuable record. There are little trapped air bubbles in the ice, trapped remnants of past climate. Plus, the chemical makeup of the ice is driven by, it's from a chemical perspective, it's the ratio of the oxygen 18 isotope to the oxygen 16, but the chemistry of the ice is temperature dependent, and we can invert for what the temperatures used to be by looking at the nature of the water and the chemicals in the air bubbles. And what do they tell us? Well, just look at the green curve. This is temperatures in Greenland, which is a good proxy for the rest of the Earth. It's not exactly right. So this is today, this is 15,000 years ago. In the medieval warm period, so that was around 980, 989, I think, is when the Vikings settled Greenland. Greenland was actually green. It wasn't a joke. It wasn't a trick to get people to stay away from Iceland. It was really green, a mossy green. A few years later, the Little Ice Age, temperature went down a couple degrees. The Vikings had to leave Greenland. As my friend says, they ate their dogs and went home. This phenomena, this little temperature change, drove a people out of its habitat. Okay? Let's go back a few years. This is what the Earth has done all by itself. Before SUVs, before coal plants. There are instabilities in the Earth's climate. Okay? 8 degrees change, maybe in a decade, maybe in 2. If this drove a people out of their habitat, what will this do? Let's go back further. Let's go back 400,000 years. This is a very familiar graph to if you've seen the Al Gore movie. And by the way, I don't have a forklift. I have a pointer. But the point here is, and I'm going to say this differently than he did. Temperatures go up and down in our past. They've done that. We know why. It has to do with the relationship between the Earth and the Sun. There are a number of what we call orbital elements, how the Earth is tilted, what is pointing to the Sun during winter versus what's pointing to the Sun during summer, and the ellipticity of the orbit, all drive these ice ages. As things have gotten warmer, more carbon dioxide has been released. Note that the temperature curve precedes the carbon dioxide curve, which is blue. That release of carbon dioxide exacerbates that warming even further. So you see the rapid rise as we reach the new state and the slow decline. It doesn't go down as quickly. The released CO2 sort of slows that decline. Up, down, up, down. This is what life has always, the planet has always done, at least in the last few 100,000 years. Here's where we are today. Instead of carbon dioxide levels being a response to increased temperatures, it's now forcing increased temperatures. Okay? So all the rules we developed, came to understand or know and love here, don't apply anymore. We're kind of in new territory. Which brings me to almost my final point. I know you're waiting for me to get there. And it's about stability of the climate. Okay? These sharp curves are indicative of unstable climates. Most of you are probably familiar with the term stability, but what it means is if you perturb a system a little bit, it returns to the state from which you perturbed it. It's like a marble in a bowl. You nudge it a little, it'll slosh around, but it'll come back to the bottom of the bowl. An unstable system is like flipping that bowl over, putting the marble on top, nudging it a little. It doesn't come back. It runs away. So the question is, does climate behave similarly? Have we been in a stable climate where the perturbations have been kind of small? We always sort of come back to this. Are there unstable climates in our past? Is it possible to push the climate state to a new unstable position? These are the questions we're faced with as the ice shrinks, because this is a major driver in the Earth's climate system. So I'm going to leave you with a few thoughts. This sort of recaps what I talked about, and then I have a parting couple of thoughts. First of all, the perspective and context offered from space is really helping us understand what's going on. The reason there's been a lot of attention on the changing ice cover is because we've been able to watch it. All of this may have been happening for ever, but we haven't seen it until recently. It continues to surprise us. Glaciers and ice sheets are contributing to sea level rise at an increasing rate. I didn't go too much into that, but the point is, more ice is melting and calving than is actually growing in the interior. And if you compare today to the 90s, it's gone up, both in Antarctica and in Greenland. Glaciers and ice sheets respond quickly to climate change. We used to think it took millennia, centuries to millennia, for a warm temperature at the surface to penetrate all that ice, make the ice a little softer, flow a little faster, melt a little quicker. Turns out it takes days. The Larsen B ice shelf collapse was instant. Okay? Again, we didn't know it could happen so quickly. Sea ice is declining substantially in the Arctic. The movies I showed you, very rapid decline. I didn't talk about it, but it's growing a little bit in the Antarctic. Again, there are reasons for that. That's a separate lecture. The impact of these changes could be large. So here's my parting thought, and then I'll take questions. Climatologically, if you remember that carbon dioxide temperature curve, we're in unfamiliar territory. We haven't been here before as a human race, at least in a way where we've analyzed it, and we just haven't been here before. There are likely surprises in our future, just as there have been surprises in our past. So the effectiveness of society's response to those changes depends on three things. It depends on how big the changes are, it depends on how fast they come, and it depends on our ability to anticipate them. And that's what all of this science, a lot of the physical aspects of the IPY, the social aspects of the IPY are as much about dealing with change that's coming. But that's what this is all about. It's about trying to figure out what's ahead, collecting the data, analyzing it, understanding the relationships between people and their environment, so that we can figure out what's coming. And hopefully, if we're smart, so that we can do things to keep what's coming from being too dramatic, too big, and too rapid. Hugely important, and it's really important that we get it right. And I'm going to come back to where I started. The Earth, the ice. I like to think of the Earth as a mosaic of stories. It's a lot of little stories. Story of the Earth, or the land, of the water, the atmosphere, telling one big story, one hugely important story. And I appreciate your taking the time to listen to what I said today, the story of the ice and how it's changing. And I hope you take with you when you leave, the sleeping giants do seem to be starting to stir. And I hope you leave with an appreciation of the importance in getting that story right. A lot of us are working hard to get that story right, to tell that story, and I'd like to thank you for listening to that story. Thank you. I don't know what you want to do about questions. Okay. All right. I'll take questions for as long as I'm allowed, and then I can take them out there. And when they kick us out there, I'll take them outside if you want. Yes.
Never once in your presentation you mentioned the word global warming. That has to be intentional.
Actually, it is intentional, but not for reasons you might think. Yeah, I'm sorry. The question was, never once in my presentation did I mention the phrase global warming. And he said that must be intentional. I kind of stay away from that, not because I'm afraid I'll get in trouble when I go back to my government office. Because, as I said, the ever-important disclaimer, these are just my opinions. I stay away from that because you start to immediately put people in a certain receptive mode, either positively or negatively, when you use that phrase. And I'd rather just tell you what's happening with the ice and lead you to wherever it is you end up. Because if I used to start talks with just saying, forget everything you know about global warming, let's just talk about ice. But now I kind of got away from that, and I prefer just to focus on what's going on, bring you to a place where you can make your own assessment. If you want my own assessment, it's real, it's happening, people are contributing quite significantly to it. That's not my own assessment, that's the assessment of scientists from 150 nations throughout the world. I mean, that debate is over. But I don't put it in the presentations because it tends to set a mood that I'd rather just be free of till the question comes up. And I appreciate your asking the question. Yes? Right. So how far could we be off and how fast? Well, could we be looking at 5 feet, 10 feet, 20 feet this century? What are the limits of the air? Okay, so the question is, I referred to potentially 1 meter of sea level rise, but there's a lot of uncertainty on that. What are the limits? What is the real limit? 1 meter, most glaciologists kind of accept as a reasonable upper limit. However, if you just do an empirical study of the past and just correlate past temperatures to past sea levels, you actually get to 2 meters, maybe 3. But our best understanding of the physics suggests it probably won't be that much. I'd say if you were to sort of poll glaciologists, what's it going to be? Very few would put it out more than 1 meter, but a lot would put it out to up to 1 meter. Now the IPCC, the Intergovernmental Panel on Climate Change, did an interesting thing. The models can't handle the stuff I showed you, the toothpaste thing and the melt ponds and all of that. And so the models just predicted without all that, and then they said, and there's this other effect that we don't know how to quantify. If we just extrapolate from today, we get to here, but it could be much worse. So it's just this huge open question. I myself don't think it would be more than 1 meter. A lot of my colleagues agree with that, but there are a few out at the 2, maybe 3. Nobody's past that, though. Yes? So are you asking about shutting down the conveyor belt? Okay. You're going to see I was prepared for all kinds of questions if I go through the remaining 40 slides I have. The question is, how long before this shuts down. Okay, I mentioned the sinking of the dense saline water, which happens. I'm not sure what I did with the pointer. Which happens. There it is. Up around here. Okay, if we suppress this, if fresh water melts in from Greenland, what happens? Do we shut down the Gulf Stream? Do we basically interrupt this? We don't know how long that would take, and we don't know how much of an input of fresh water it would take to do that. This is we used to know, but now that we've learned more, we don't know. That's very common in science, actually. So I really don't have an answer to your question. There's still some debate as to whether that would even happen. Okay, but the point is, there have been abrupt changes in our past. The most rapidly changing aspect of the Earth system is its ice. It's logical to conclude there's a coupling between the two. Yes?
Will part of sea level rise be due to warming of the ocean? How does that compare to the melting of the ocean?
Yes. The question is, will part of the sea level rise be due to the expansion of the ocean as it warms? I think right now they're ascribing, over the last century, between half to a third of the current sea level rise is expansion of the ocean. But there are limits to how much the ocean can expand. You know, it can't really, no matter how hot you make it, it can't really get much more than a meter in height. Contrast that with, 70 meters from the land ice, and it's hugely important for the coming century, but the elephant in the room is the ice sheets. Yes?
One of your slides showed Greenland, the interior being below sea level.
Yes.
And I've heard or read that, especially in Antarctica, the center is about a mile below sea level because of the weight of the glacier. I'm wondering if, as the glacier melts or is displaced in Greenland, would the land level pop up? Would that have any effect on sea level?
I can't get past this slide. Yes, the question was, okay, a lot of Antarctica, a lot of Greenland are below sea level. As that ice melts, that depression that's a result of the weight of the ice will be lessened, so won't that start to rise and mitigate the effect that I was referring to? Yes, but not until a lot of damage has been done. If we lose the equivalent of a meter of sea level from Greenland, then it'll start to slow down, as that uplift starts to raise the basin from below sea level to above sea level. But there's a lot of potential sea level between now and then. And in the case of Antarctica, it's not on the West Antarctic Ice Sheet. I don't think it's so much attributable to the weight of the ice. I think that's the topography. That's just, I may be wrong about that, but in Greenland, what you said is true, but in Antarctica, I don't think that's so much true. Yes?
I've heard some people say that in Antarctica, the West Antarctic Ice Sheet is losing ice. The East is actually gaining because it's colder, and so the ice is accumulating. But apparently your gravity measurements and naked laser measurements mean that there isn't actually a net loss from the whole of Antarctica. Is that right?
Yes. East Antarctica is about in balance. It's gaining about as much as it's losing at the edges. West Antarctica is out of balance, so the net combined effect is loss from Antarctica. The conventional thinking years ago, actually not that many years ago, was that Antarctica is so far below freezing that as it warms, it'll snow more, but it won't melt more, so it should grow, offsetting whatever shrinkage happens in Greenland. But because of the dynamic effects, that's not the case. Yeah, in the simplest sense, the nature, Antarctica is set right on the pole, and it sort of sets up its own climate. Reduced ozone layers and the nature of atmospheric circulation are such that if this is Antarctica and this is the peninsula, there's a very strong vortex circulating around the continent, which prohibits lower latitude air from it's like a wall, a barrier from penetrating that. So parts of Antarctica have really been able to cool, whereas the peninsula that sticks out from that has been warming substantially. No, actually, I'm sorry, yes, that is contributing to it. As ozone recovers, you fix one thing, you create another problem. That should change. Yes? Oh, sure. Boy, how much of the territory of the Arctic is unclaimed? You're referring to the land territory, I assume. I don't think there's any that's unclaimed. There are parts of Alaska you can still homestead, but it's part of the United States. Canada has its own. Right now, the race is to claim the ocean, as the resources become exposed and people want to plant or have planted flags at the bottom of the Arctic Ocean. But land area is all spoken for.
Another question that we've received, what's the state of collaboration among the scientific community on this issue, and who needs to be a part of the conversation that is currently not in it?
Okay, what is the state of collaboration among the scientific community on this issue? Let me tackle that first. In a word, improving. And it's improving because of the International Polar Year. I mean, it's by design set up to encourage people who may not have taken the initiative on their own to interact with colleagues all over the world. These projects really are multinational projects that are intended to leave a legacy, just like the last one in the International Geophysical Year, where Antarctica was explored, discoveries occurred, left a legacy for generations to come. So there's a lot of there always has been good international interaction, but I think it's getting better by virtue of the IPY. The second question, or part of that question, was who is not engaged in the conversations that should be? Well, I can't speak to who's engaged and who's not, but what I will say is we should all be engaged. I mean, this is the kind of thing, I don't like to scare people. I've actually been accused of not giving scary enough talks. So if you're not scared, I'm sorry. But I don't think it's constructive to say, we're doomed and we got to do something, this is horrible. If I could grab the world by its lapels and shake them and say something, I would say, pay attention to this, because we got to figure it out. And the way we figure it out is by everybody trying to understand. Have a conversation with your neighbor, with your kids, with your senator. Sure, I'll say it. Vote, the way you want to vote. It needs to be a national consciousness. And the reason I give talks like this is because I really think it's hugely important to elevate the scientific literacy of people on the matter of global change, global warming, whatever we want to call it. So we should all be engaged. I think most people, well, I don't know who's not engaged, so I can't answer that, but more of us need to be. Sorry, that's kind of a cop-out. I'd like to say 10 years from now we'll have it all figured out and we can move on to other problems. But it's the classic, the more you know, the more you realize you don't know. So I think a good analogy is weather. Okay, we're talking about climate change. Let's look at weather prediction in the 60s and 70s. Okay, you couldn't trust tomorrow's forecast, much less 3 days out. What are you, crazy? Why even try? Now we're good for about a week. Reasonable, within limits. Climate, and that took 20, 30 years, a lot of satellite data, the context, scale, and perspective, a lot of computer models. I think climate, we're on a similar trajectory, and I think we've made huge advances in the last decade, and I think in the coming decade, we're sort of about shrinking that uncertainty. I think we're going to get better, but when we're good enough to have the answers, I don't know, but I'll tell you this. I think if we wait till we're good enough to have those answers unequivocally, it'll be too late to do something about it. You know, I tell a story sometimes when I was a young engineer, and this is probably one of the reasons I went back to grad school, is what I'm about to tell you. One of the first things I did was monitor an environmental test of a satellite. We put it in a heating chamber, and I was supposed to watch the temperature rise. My only job was to not let it get above X or below Y. That was it. And I worked through the night, 24 hours watching this test, and temperature was going up, and I thought, I don't see a problem here. I'm going to go get a soda, and the soda was at the other end of the building, and I went and got my soda, and I came back, and the thing was red lining. Well, orange lining. If it was red, it would have been fired, but it was getting hotter than it should have been. So I turned down the temperature. And it's like when you put a turkey in the oven at 350 degrees, okay? Once it gets to the desired 180 degrees and you turn off the oven, it still heats, just like my satellite, just like the Earth. Okay, we've already sort of set the trajectory for the coming few decades. Where was I? Getting a soda. It was then I decided to go back to grad school and try and tell the world not to make that same mistake. Yes? How long is it before the next ice age? That depends in part on what we do with greenhouse gases. In the 1970s, and this gets a lot of press, there was a small group of people, scientists, that thought, hey, these things, this particular cycle occurs on about 19,000-year timescales. It's been, 15, 18,000 since we came out of the last one. We're probably headed into another one. But as we've learned more, we're sort of in a level area, and we probably wouldn't be headed into another one, and we're certainly not headed into another one because the greenhouse gases are a more dominant effect. So if we stopped greenhouse gas emissions, and sort of just turned all that away, we'd probably head into another ice age. My paleoclimate's not that good, but on the order of 10,000 or more years. So nothing you need to worry about. Yes?
We hear a lot less about global warming.
Yeah. If global dimming were not happening, we'd be worse off? Yeah. It is. The question, global dimming, first of all, is that there's more stuff in the atmosphere, and the Earth is not as bright as it once was. And that stuff filters out incoming sunlight. And the question is, if we fix that problem, will the Earth get warmer? Yes. I mean, you add increased insolation to the surface of the Earth, the temperature will go up, but that's less of an effect than the absorption of heat by heat-trapping greenhouse gases. So it's a much smaller effect. Okay, I feel the vaudeville cane about to come out. Should I take one more? Okay, I think, go ahead. The question is, why is sea ice thickest near Greenland? I think for that I can actually go to my... It has to do with a few things. It has to do with the ocean circulation patterns. As you have a low system that tends to center over the Arctic, creates a polar vortex that kind of piles ice up. Oh, I have the pointer. Piles ice up in this area here. And this is, I'm not sure, but I think this is a little bit colder than this area here. But in the ocean, you have the intrusion of warm water from low latitudes here, which starts to erode or cut away at this. So ocean circulation is really chipping away here, atmospheric circulation elsewhere in the Arctic, and you have kind of it's a thermodynamic and dynamic effect, the movement of ice there and the nature of how it freezes on the underside because of the ocean circulation. But I'm not really an oceanographer, so there's probably a better answer than what I just gave you, but that's the best you'll get from me. All right, well, thank you. I appreciate your attention again, and I'll stick around.
Thanks very much indeed, Waleed. It was really an outstanding lecture. Just a couple of other points, acknowledgments really. First one is I would very much like to say thank you to the staff of the Roselle Center for doing an outstanding job of setting this thing up. And all right. And the second one is that despite the fact that they're a publicity outfit, they really operate behind the scenes an awful lot. The UD Office of Public Relations has just done a tremendous job with not just the Carlson series, but IPY in general. And specifically, I would like to point out someone who's working here. Well, she sits in the front row, Tracy Bryant of the Office of Public Relations, who's been handling, as you probably heard, the questions from Second Life, but has been doing an absolutely outstanding job with the website, with the U Daily articles, and a lot of behind-the-scenes logistical arrangements. So we're very much in your debt, Tracy, and thank you.